Hello everyone, thank you for coming. I am quite flattered. And at the very beginning I would like to make a couple of disclaimers. The first one, the program changed the font, so it will get very ugly very soon. The second one, this is my first talk in front of the audience ever, so please be gentle. And the third one is, my background is in veterinary medicine. I am not a cognitive scientist, but I think you've heard quite a lot about cognitive science during this gathering. And I am going to talk more about anatomy and maybe a bit histology. So also it will be not very comprehensive. In the course of preparing the presentation, I realized that I should probably change the name to something more like this. And the reason is quite obvious, I think. Neuroscience is vast. It's really vast. To show you how vast it is, I prepared a graph. This is the so-called T-SNE plot, and it is showing the groups of topics that were talked about during last year's SFN meeting. And if you wonder what an SFN meeting is more or less like the Polyglot gathering, but 50 times bigger. So more or less the population of San Marino coming to one place and talking about neuroscience. And you can see here, for example, this group of dots. This is my field of interest, this is epilepsy. And this little dot here is the human language. And today we are going to talk about, I don't know, a fraction of a millionth of a pixel on this dot, but maybe we will get a glimpse into how the brain is structured and which structures are responsible for talking. Okay, so let's get started. I told you the font will get ugly, sorry. I would like to show you also a bit how a lecture in a medical school looks like. So usually you get a clinical case at the very beginning of the lecture, and later you are going to learn from that. So you have a patient. He's an adult, young adult. He's a male. In my field, in veterinary medicine, we would probably indicate whether he was castrated or not, but let's assume he wasn't. He was a physical worker, probably illiterate or to some extent literate. What's interesting for me, he was epileptic since his young age, and he was presented to the hospital because he lost an ability to speak. At the beginning it was quite mild, later it got gradually worse and worse, and in the end he was able only to speak one syllable, and it was tan, or ton because he was French. After 10 years of onset of the first symptom, it got even worse. He started to deteriorate mentally. He developed problems with vision, especially in his right eye. And he developed the paralysis of the right arm and right leg. Later, he developed also phlegmon. It's a medical state where the pus is gathering under the skin. It's not very nice. And he got transferred to another hospital, which was not very good for him, I guess, but it was very good for neuroscience. Because he was taken care of by a quite curious doctor. He was a surgeon. He examined the patient. He realized that his left arm and left leg are without any abnormalities. His cranial nerves are also fine, so the movements of the eyes, the movements of mouth and tongue, no strabismus, no nystagmus, facial expression was okay. This is basically how they communicated with each other. And his bowels and internal organs were also fine. The patient died, and our doctor, because he was not only a surgeon and he was not only a neurologist, he was also a pathologist, like many of 19th century doctors were. He examined the patient post-mortem. What he found was a cavity filled with a clear fluid, more or less between the frontal and the temporal lobe, And in the same place, there was a volume loss, generally speaking, neurodegeneration. Also in some perifrontal regions located deeper in the brain. And also the brain has a lowered mass as compared to a standard male at the same age, at the same size. What our doctor figured was there was probably an ischemic insult, so probably a stroke, and later it led to a neurodegeneration. If any of you is interested in neuroscience, you probably know the name. So this is our doctor, and we don't have a picture of the patient, but we have a picture of his brain. And this is this chicken egg-sized cavity I was talking about. So our doctor, who basing not only on this case, but also on other cases, figured out that probably this region is important for speaking. And he was right. What he also figured out was that this region is always located in the left hemisphere. And he was also right in the most cases. And later on, another neurologist, a German, he described another also very important region for speaking, and also described the whole loop called later Wernicke-Geschwind loop. So briefly, we get the input from directly from the ear, strictly to the primary auditory cortex. From the primary auditory cortex, it goes to Wernicke's area located here. And this area more or less serves as a processor. Later, over arcuate fasciculus, back then believed to be unilateral, the signal goes to the Broca's area, which is important for generating the speech, and the signal goes to the motor cortex that is controlling the movement of muscles of mouth, of tongue, and so on. So let's get a closer look on those areas. The Broca's area, generally speaking, as you can see, is important for selecting the phonemes, later putting them together into words, and then putting words according to grammatical rules into sentences. It is also quite important for rhythmicity of speech, generally speaking, yes, and generation of speech. If we have any dysfunction in this area, and generally speaking in any area responsible for speaking, we get a condition called aphasia. And this is an impairment of language, which is regardless of whether it's affecting the production or the comprehension, and whether it's regarding speaking and hearing, or reading or talking, writing. Because some people also believe alexia, dyslexia, agraphia, and so on to be aphasia. So in the case of dysfunction of Broca's area, we will have obviously a Broca's aphasia. And in this case, we'll have difficulties with assessing grammar, difficulties with naming stuff, and articulation problems. And let's hear an example.
Now tell me what this thing was with your legs last week or week before.
No good. Ache and
So you can see that the patient is talking slowly. The speech is very labored.
and ankles.
What'd you do about it?
doctor and legs walking no good.
No good, huh? Man, you're a fellow who likes to walk, too.
Oh,
Jeff.
geez.
Huh?
Oh, boy, oh, boy.
And it's getting too cold
Yeah,
to run your John Deere tractor, isn't
Yeah,
it? Up and
yeah.
downtown.
yeah.
What'd the doctor tell you, Jack?
Don't know.
He doesn't know what's going on,
No.
huh?
No.
Did you feel sick in any other way?
No. No. Ache.
Yeah. Legs ached.
Yeah.
Did you feel weak?
No.
Maybe you had a touch of rheumatiz.
Don't know. Let's see.
Okay, so you can see speech slow, labored, articulation problems, no intonation, escaping to keywords. So it's often described as a telegraphic style of talking. So you get what the patient is talking about, but he's using only some catchwords like legs, hurt, not so good. But he understands the questions from the speaker, and he can answer. He can communicate. In case of Wernicke's area, it is a bit different. It is all often very often described as a part of the brain that's responsible for understanding, but it's more like processing. It's more like deconvoluting the signal from the ears and recognizing phonemes and words. It's also quite important for analyzing spatial and temporal changes in the auditory input. So this is this famous case, because the sentence is not the string of words or string of phonemes. There's also some breaks that can change the sense of the sentence. And this is also other case. This is also Wernicke's area is also responsible for recognizing the consonants that have very fast onset. For example, p, t, d, and so on. So patients who have dysfunction in this area will be not able to distinguish them. So you can also make an experiment when you put your hand on your neck and say p. You can feel the difference between a small time interval between opening your mouth and movement of your vocal cords. And if you do the same and say b, this interval is almost imperceptible. And this is the difference that is not possible to be grasped by people with Wernicke's aphasia, for example. But this is also the thing that you can know from your everyday life, because it's exactly the case of misheard lyrics. Okay, so in Wernicke's aphasia, we will have reduced speech comprehension because our processor is not working well, and the speech will be fluent and mostly intact because there's no problem with generation of the speech. And here is the example.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment and talked with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck for him.
So we're on a cruise and we're about to
We
get to
will
Juneau.
store it right here and they'll save their hands right there for them.
And what were we just doing with the iPad?
Right at the moment, they don't show a darn thing.
With the iPad that we were doing. Like here?
I'd like my change for me and change hands for me. It would happen. I would talk with Donna sometimes. We're out with them. Other people are working with them. I'm very happy with them.
Good.
This girl was very good and happy. And I play golf and hit other trees. We play out with the hands. We save a lot of hands on hold for peoples, for us, other hands. I don't know what you get, but I talk with a lot of hand for him. Sometime. Am I talk of any more to saying?
All right. Thank you very much.
Thank you very much. I appreciate it, and I hope the world lasts for you.
Thank you. It's been a pleasure. Bye-bye.
Have a good day.
Okay, so the first comment under this video is he sounds like a politician. There's something to that. But you can see that the speech is really, the content is not is unintelligible, but the production is very good. And once again, the comparison between Broca's and Wernicke's aphasias, there are much more other types, but these two are the most popular and the best studied. So we have slow halting speech, disordered syntax, grammar, and structure of sentences, and the comprehension is okay. And here we have fluent speech, grammar adequate, and syntax adequate, but comprehension is not intact. Okay. So some anatomists distinguish another, let's say, a higher level to the Wernicke's area, another region of the brain, a so-called posterior speech area. So this is this pinky stuff around, and this is if Wernicke's area helps recognizing phonemes and words, this area helps associating it with the meaning. So in the case of any dysfunction in this area, we will not have a clear aphasia, but we will have some smaller problems, like problems with word finding. For example, longer pauses during conversations, repetitions, escaping to catch words like, you know. Some people can, for example, suddenly stop the sentence in the middle and start talking about something completely unrelated, and escaping to gestures or facial expression instead of speech. And also we can have some problems with paraphasias. There are two types of paraphasias. One is semantic, so replacing a word with another word that has similar meaning, and phonematic, so replacing one phoneme or replacing the whole word that sounds similarly. Okay, so this was it about the diseases of the brain related to the speech. Let's talk about lateralization, because it's quite an interesting concept. I think this is obvious that language is performed by the whole brain, not just a couple of regions we've been talking about. But there are some essential regions in this network, and they tend to lateralize to one hemisphere. And why this? We have three types of lateralization. One is the typical lateralization, so the left dominance, and this is the case in most people. And there's also an ambilateralization, so there is no dominant hemisphere, and also an atypical lateralization with the clear right hemisphere dominance. And I've written here 0% of right-handers, but it's obviously not true. There are some people that are right-handed and right, let's say, brained in case of the language, but there is a correlation with left-handedness and right-braininess in case of language. So there are more lefties that can be right-brained, let's say. And why bother? Why would evolution lead to gathering all the crucial regions for speaking in one place? Well, one thing is we are avoiding processing delays, so one neuron on one side of the brain doesn't have to wait for the signal from the other neuron from the completely other side of the brain to fire a signal. The other thing is we are not using so much neurons in the brain, so they can be used for other processes. So, as my boss probably would say, it's all about sparen. We can test lateralization. Well, why would we do that, generally speaking? It's important in neurosurgery. Let's get back for a minute for epilepsy, to epilepsy. Sometimes in people who have really severe epilepsy, which is pharmacoresistant, you have to cut out the epileptic focus. So in this case, you have to know exactly in which hemisphere of the brain the language center is located to not cut it out with the epileptic focus, because epileptic focus is very often located in the temporal lobe, and in temporal lobe we have all our language centers. So one test for that, one assay for that is so-called WADA test. It is very old test and very simple one also. We have a patient who is performing some simple cognitive task like counting down, and we get he or she gets an injection into a carotid artery, so the main artery that is supplying the brain. There are two carotid arteries in the neck. One is supplying the right one is supplying the right hemisphere, and left one is supplying the left. They are not mixing. So we can be sure that if we inject an anesthetic into the right hemisphere, it will into the right artery, it will get to the right hemisphere. So it's quite simple. If the patient gets the injection into the artery supplying non-dominant hemisphere, he or she will continue the task, and if they receive the injection into the dominant one, they will cease talking. Quite simple. Okay, the other one is so-called dichotic listening, and it's based on the principle that the signal from the right ear is mostly processed by left hemisphere, and from the left ear in the right one. So the patient is having headphones on and receives two different signals to both ears, but they are, let's say, similar enough. So the signal he or she reports indicates which hemisphere is dominant. And there are two models to explain that. One is that there is somehow longer way from the non-dominant hemisphere to go to the dominant hemisphere, so it's based on an anatomy of the brain. And the other one is based of the priming of the brain. So the dominant hemisphere is learning faster to react to the signal. So that's why this one is reported. Okay. There are also some imaging techniques. You can also, basing on the principle that the organ that is working receives more blood. You can do a simple Doppler sonography, so we like ultrasonography, but with measurement of the blood flow. But it's also only showing which hemisphere is activated. If you want to have a higher resolution, you can do a functional magnetic resonance imaging. And here is the MRI signal from a brain in the relaxed state, and here is while performing some language-related tasks. So you can see the difference between the activation, and also you can see which part of the brain is more activated. And if you want to add a temporal dimension, you can always do the old good EEG. Okay, so we've been talking a lot about the dominant hemisphere, so what about the non-dominant one? Because it's also contributing to the language. The right hemisphere is very often described as the emotional one, as in contrast to the left hemisphere, which is more analytical, and it's really the case in language. So the non-dominant hemisphere is responsible for the prosodic characteristics of the language, so the musicality of speech, comprehending the tonal changes, the intonation, the pitch, and the timbre of the voice. But also the pragmatics, so whether the speech is comprehensive, whether it makes sense, the conversation makes sense, or I don't know, whether we are using the the correct language for the correct situation. So very often people with problems in the right hemisphere will be perceived as odd, or maybe as rude, or maybe will not get the point of the joke. And also all around the language, so around the content of the speech, so emotional tone and so on. And if you remember the slide from the very beginning with this Wernicke-Geschwind loop, in the last years there is something more to that, let's say, after all the studies. So this is still true. This is this loop we've been talking about at the very beginning, the primary auditory cortex, the Wernicke area, the Broca area, and the motor cortex. This is still true, but it's, let's say, implementation system of the implementation system of the language. But there's another layer to that. There's so-called ventral stream. And it's activated bilaterally, as you can see. And this is it's connecting the auditory areas, the primary and secondary cortex, with regions which are responsible for memory, with conceptual memory, and with knowledge. But I believe this is a story for another time. Thank you. Any questions?
So thank you very much. So there are quite a few questions. So the first one is a Broca patient able to write normally?
Yes, because reading and writing is involving another regions in the brain. This is not completely related to the talking and the hearing. So reading is not involving Broca's area.
How does the brain of bilingually or multilingually raised kids differ from a normal one? With
Okay, that's a good question. So in the bilinguals and multilinguals, the brain is involving, let's say, it's not involving only one hemisphere. There is a tendency to involve the second one. So this is this ambilateralization case we've been talking about. But also, not in the case of children, but in case of people who are learning the language, with the increasing proficiency, the languages spoken on the proficient level tend also to be lateralized to one hemisphere. So at the beginning, if you learn a language, you are using both hemispheres, but later it goes, so to say, to the only one. And it's explained that with increasing proficiency, you are not relying that much on those prosodic, paralingual cues from the non-dominant hemisphere. So yes, let's say.
Can other areas of the brain take over in case something goes wrong?
Okay. Well, not really. Not in all the cases. Well, you've seen the examples of patients that something went wrong and they were not able to speak normally. But if for example, if there is a stroke or other insult in the brain, it can be the case that one language is saved because they are. If you speak multiple languages, they are stored. Let's say stored in different compartments. So it's possible that you will develop a deficiency, but only in one language.
Do other primates display similar brain activity in corresponding areas when communicating? What about other mammals?
Primates. A good question. I don't know about primates, but the similar patterns is found in birds. In case of bird songs, I believe it would be a case also in primates, but not to the same extent as in birds, because bird songs are very complicated. They also are very often compared to human language, and the birds are basically the model for researching human language. So I would say yes, in animals, yes, but I don't know about primates.
What can cause aphasia? Is it reversible?
So yes, generally speaking, most cases, the most popular neurological disease in humans is stroke, and this is also the most common reason for developing aphasia. Also epilepsy, very severe epileptic patients can have problems with talking. Also, I believe there is a genetic condition that is causing the general aphasia, so not related to any region, any specific region, but it's more like a general inability to speak. So many reasons. And what was the second part? It also depends on the severity of the condition. So if a patient has a stroke, for example, you can work on that. You can have a patient that is completely not talking, and with a good logopedist, you can, to some extent, reverse it. But it's not 100% in all cases reversible.
How to apply this kind of knowledge into learning?
I don't know. It's, let's say, application to learning is more related to the cognitive science, like yesterday's lecture of Professor Keeley. This is more just to show you that there are some structures in the brain that are responsible for language formation. I don't believe you can really, focusing on Wernicke's area, learn better a language or something like that. But well, you can try to, by learning a language, you can surely make your brain better, let's say. You can increase your neurogenesis, adult neurogenesis in hippocampus, and by learning a language, learning a language is influencing the other parts of the brain. So I would say it could work in the other way around. So if you are generally speaking learning something, you will also learn better languages.
Do speakers of tonal languages distribute language processing regarding tones differently with relation to dominant and non-dominant hemispheres?
I don't know if there are studies comparing tonal and non-tonal languages, but it would be interesting. It would be interesting to see whether they use the right hemisphere more than the other speakers. But I don't know any studies about it. Sorry.
Any correlation with learning languages and preventing mental deterioration?
Yes, in fact, yes. As I mentioned, learning in any way, learning anything, but predominantly learning the language is increasing the adult neurogenesis. So you get more neurons, because it's not true that you are born with a certain amount of neurons for your whole life. There are still neurons produced in your brain, even now, and this is the amount of the neurons and also the amount of synapses, so connections between them is helping in keeping your brain healthy in the old age as well. But there are no, for example, there is no connection between, I don't know, learning languages and preventing Alzheimer. But another type of dementia, I think so.
Okay, and now the patient lost his ability to speak, but did he retain his ability to understand spoken language? I think it refers to the first case you presented.
Yes. So, in case of Broca's aphasia, the comprehension of the speech is intact. So the patient understands what the other person is talking to him and also understands what he is trying to communicate, but he is not able to do it. So it's quite painful actually to watch, as in the case of the first video. This is also the case that the patients with Broca's aphasia, if they are presented a word, they are able to repeat it. And in case of patients with Wernicke's aphasia or general aphasia, they are just talking random stuff. They are not able to repeat the word.
Is there a non-invasive way to test the dominant hemisphere?
Yeah. So the only invasive way is the WADA testing. The non-invasive is all the imaging. So MRI is not invasive. MRI is only the patient is scanned by the giant machine, is exerting the magnetic field, and you are observing the changes of the blood flow in the brain in the course of time. So it's not invasive unless you are using contrast. And yes, so generally speaking, this is the most often used, because the WADA test, it was used more often in 70s or in 80s. Now it's more, the weight is more shifted to the imaging.
Is anything that is generally improving brain function, like breathing oxygen, would increase the efficiency of learning languages?
Sure. I don't understand the question. So, like breathing, any special types of breathing or normal breathing? Who asked the question? Okay, so well, yes. If you have a higher oxygen level, your brain is working better. So for sure, that would improve your learning skills. So yes, but I don't know any special techniques that would improve, breathing techniques that would improve learning languages.
So this is not really a question, but a note. Someone noted that there was at least one study linking multilingualism with delayed onset of dementia. There are previous Polyglot conference and gathering videos on that.
Okay, so
I've seen people quoting 4 years.
Excuse me?
I've heard people quoting 4 years.
Okay, good. Okay. But was it Alzheimer or was it just standard old dementia? Was it Alzheimer dementia? Okay. Yeah. Because it depends, because Alzheimer is based on somewhat different mechanism. There are standard senile dementia, sorry.
Yeah, there are still questions coming. Is there a reliable cognitive test to test the dominance as well? For instance, one that doesn't need equipment?
I would say not really, because you have to have a neutral observator, let's say, or a neutral machine that is doing the measurement. You cannot assess it by yourself. And I would say you don't really need it. I know it would be interesting to know whether I am right-brained in case of language or not, but this is only useful for people who have really problems with the brain that need the neurosurgery, for example, and have to have this region saved. I don't think so.
So I think this was the last question. So does anyone else have any question? So okay. So thank you, Marta.